Hello, everyone. Welcome to Free GMAT Prep Hour. Let me know in chat if you can hear me. Can you hear me? I don't sound very loud to myself today. It's interesting, but good to know you can hear me. That's all that matters. Thanks for tuning in. November 22nd, 2020 edition Free GMAT Prep Hour. Just a reminder, we come with another edition of this just about every 2 weeks. We try to get 2 of these in per month. So try to tune in into our December episodes. I know I'm doing one of them. I think December 20th I'm on, and someone else is doing one a couple weeks before that. Very glad to have you here. If you're in chat, just go quickly, just say hi. Let me know where you're from if you haven't already. I see we've got people from other places in the US, Toronto, India. Great to have you here. Sweden, love it. This is truly an international group. Thank you for staying up so late in Sweden to listen to me ramble. Reminder, you have some other options for free prep. Please come to one of our session ones. Try it out, see if it's for you. Learn about some things related to data sufficiency and sentence correction. Really, really important, especially if you're just getting started. Also learn a little bit about how the exam is scored and what's on it, and how you have to change your mindset to best succeed on this exam. This is a different exam. The GMAT is different from just about any other exam you've ever taken. And you want to kind of understand how those differences will affect the way your score is computed and the way you need to prepare. You could also check out our Interact course called GMAT Interact. Go ahead and try that out too. Visit our website for some more details, but let's get to the content for today. Yeah, I'm trying to monitor chat as it goes. We'll see what we can get to. Yeah, I'm gonna just go ahead and address something right now. Questions about reading comp. Here's what I'll say about reading comp. You notice today is not about reading comp, but I'm gonna make a digression. The best reading comp passages that you can practice on are official guide reading comp passages. You know, it's just hard to make better passages or find better passages and ask more official guide-like questions than the official guide can do. And so those are going to be your best resources for tackling reading comp. There's often questions about, free GMAT prep hours on reading comp. What I'll say is we are somewhat limited in how much reading comp we can do, not just because it's like a tricky topic to teach, but because there's just limited resources we're allowed to use that are really, really good, right? We're only allowed to use some of the official resources because most of those official resources you have to pay for. There are some free resources, so you can exhaust that pretty quickly. And then most other resources just like aren't going to be as good as the official stuff. So that's a little bit why there's a logjam in reading comp. I do think you can practice reading comp. I mean, I think it could be helpful to look at some other videos. Like I'm getting questions about the GRE reading comp videos, the LSAT reading comp videos. And yeah, those would be valuable. Anything that helps you think about how to read better and how to answer questions better is great, but the best resources are going to be the official ones related to the GMAT. Awesome. Let's go tackle exponent stuff today. Yeah, I think we're going to start with some basics. Obviously, this is kind of how I like to start my lessons, and here is start with some basics and try to climb the mountains. We're going to start with just some exponent fundamentals. Make sure you understand your rules for simplifying, and then we'll try applying those to topics or harder and harder questions related to exponents, and then try to fold in some other things like number properties. So I'm going to go ahead and leave these 8 little exercises up here for, I don't know, a minute and a half, 2 minutes, and see if you can simplify them or rewrite them in a different format. Don't need to tell me what the answers are in chat. We'll find out the answers soon enough. I'll give you about 90 seconds to think through these. Give you another 30 seconds here. All right, it's been about 90 seconds. Hopefully not too many of these simplifications are too tough. If they are, we really want to learn these lessons because, you know, learning how to simplify exponential expressions like this, or expressions involving exponents and bases, really going to be essential for more and more GMAT mastery. Okay, oftentimes they won't just give you a plain old exponent question like this. They'll rope it into another type of question, but this is the prereq, right? We have to know how to do these to have a chance. So x to the 5th over x squared will be x to the 3rd. And the easiest way to kind of like clear up any confusion of exponents like this is just to write them out. Okay, just list them out. Oh, I have 5 x's multiplied through the top. I have a couple in the bottom. If I write it like this, it becomes pretty easy to see that a pair of x's in the top cancel with the pair of x's in the bottom, and this will be x to the 3rd. It's an ugly 3. That should be a 3. All right, x to the 3rd times x to the 5th, right? If here we canceled out 2, and so in effect you're subtracting 2 from 5 to get 3. Here we're going to add them. And again, the best way to see that is to list these out. Like x to the 3rd is x times x times x. And x to the 5th is, well, I feel ridiculous saying it, but it looks like that. And so put that all together, what do you have? You have 8 x's being multiplied by each other, and that will be x to the 8th. All right, so that's why you add them here, and that's why you subtract them here. If you're fuzzy on that concept at all, write it out and convince yourself of why it's true. xy all squared, that will be x squared y squared. And again, if you're not sure about this, write it out, right? That's going to be kind of how you convince yourself of these rules, is to just, you know, do it the long way enough until you really believe in the shortcut, right? xy squared is, well, that's xy times itself. Without the parentheses, that's x times y times x times y. And in multiplication, it doesn't matter the order in which you do this. So that's going to be the same as x times y, hence x squared, y squared. This one down here, is this the one where I add the exponents or I multiply them, or do I raise 2 to the 3rd? If you're not sure, again, what am I going to say? Write it out, right? You have x squared times x squared times x squared, right? We're taking this term here and cubing it. That looks like this. Write those out. X squared is x times x. So is this x squared, and so is the next one. What do we got? You have 6 x's, and that is why these multiply, okay? And you can convince yourself of it by just writing it out, okay? So the next time you see something like x to the 5th to the 11th, okay, that's going to take too long to write out, but just try something like this. Oh, do I multiply these? Do I add them? Do I raise 2 to the 3rd? Oh, it looks like I multiplied them here. I would multiply them here as well. Anything to the 0th power is 1, except maybe 0 to the 0th power. You know what? Don't test me on that one. That's kind of, to me, that's where like math breaks. Not really sure how that works. But x to the 0 is going to be 1 as long as x is not 0. X to a negative power, we can rewrite x to the negative 6th as x to the positive 6th in the bottom of a fraction. Okay, so that's how we can kind of shift from negative exponents to positive exponents, rewrite it as the positive exponent version, but kind of flip the fraction component that you'd find it in. Okay. xy cubed over xy squared. What we're going to do here is apply kind of this principle, and then we're going to apply this principle. All right, so stacking multiple exponent principles. That should be x to the third, y to the third over x y squared. Now we have to be careful here. X y squared is not the same as xy squared. Those are different, right? The y is squared here, but the x is not, because in your order of operations, exponents are applied before multiplication. The reason that the squared here applies to the x as well is because first you do parentheses before you get to exponents. So what we're going to do is we're going to simplify some of these things. X cubed over x simplifies to x squared. Y cubed over y squared simplifies to y. So all of these things stacked together, just go ahead and delete that, should leave you with 2 factors of x and only 1 factor of y, x squared y. And then finally, in the last one, we've got negative exponents and we've got some division here. So what we're going to do is we're going to take this xy to the negative second and write it as xy to the positive second in the other half of the fraction. We are going to write x to the negative first as x to the positive first, which is just x in the top of the fraction. All right, remember, we get to, thanks, Chris, appreciate that. We get to rewrite these exponents as the positive versions as long as we switch which half of the fraction they're in, okay? And now we're going to simplify. This is x over x squared y squared. One of these x's will cancel out. And so that should be left as 1 over x y squared. Running out of room. Running out of room. But there we go. Cool. All right. So if these are a little rusty, I'm going to very much ask you to drill these topics. You can drill these via our Foundations of Math book. There's lots of other resources on, exponent simplification. This is worth your time. Exponents are a question type that are common enough that you will see a return on this investment. Okay. All right. Let me just ask quickly, any questions in chat before we dive into the harder questions? I don't think you really need to know that. JD question came in like, do you need to know how to graph x squared or x to the third? I don't think you really need to know. I think it could be helpful to know their general shapes and some of the principles about those, but I don't think you need to know. And you definitely don't need to know like vertical shifts and horizontal shifts and skews and, stretches and factors of stretches and things like that that you had to learn in like Algebra 1 and Algebra 2. All right, let's go take a look at some questions. I've got a sheet of 4, you can see exponent-y questions here. I'm going to go ahead and give you 8 minutes to think through these. If you're watching on YouTube, I'm going to try my best to make this 8 minutes so you could leap ahead if you want to pause it here. But 8 minutes starting now. When you're done, just let me know you're done in chat. That's been 2 minutes. If you have questions, feel free to ask them to me in chat. I'm answering questions right now, so get in here if you want to. It's been 4 minutes. You have 4 minutes left. Got about 90 seconds left. If you finished, I sent you a bonus problem. You got 30 seconds left. All right, that has been 8 minutes. 8 minutes is up. Let's go tackle these. Let's do the first one because it's first. This problem's interesting, okay? It is no coincidence that there are 4 to the 5ths here, okay? If you, go ahead and tell me privately in chat what you got for this problem. What'd you get for this problem? Okay, we're like stuck between like 2 answers based on what I'm getting in chat. Okay, mostly. I'm glad no one's picking answer A, which is good. I think you can eliminate answer A like a couple ways. I think answer A is just like way too big. Okay, like where is 625 coming from? 625 is 5 to the 4th power. Do you need to know that? No, but that's where 625 is coming from. Guys, 4 to the 5th is like not too big a number, right? Like we know 4 to the 1st is 4 and 4 squared is 16. And I would say you should probably at least know 4 to the 3rd, 64. But 4 to the 4th, even if you don't know exactly what it is, you'd say, well, 4 times 60 is 240. So this is about 250. It's literally 256. It's exactly 256. But if you know it's about 250, then you know 4 to the 5th is about 1,000. And so if these are each 1,000, you add them all up, you'd say, yeah, that's about 4,000. I don't know what 4 to the 625th is. It is way more than 4,000. It's just so much larger than 4,000. This is larger than a Google, like way larger than a Google. All right. So I can't even describe how big a Google is. But this is way larger than that. This has got to go. 4 to the 20th, that's an answer that's coming into chat a bit. 4 to the 20th would be correct if these weren't addition signs and they were plus sign, or they were multiplication signs, right? If you had 4 to the 5th times 4 to the 5th, we just looked on the other page. We said, oh, x to the 3rd times x to the 5th is x to the 8th. So 4 to the 5th times 4 to the 5th would be 4 to the 10th. And if you did that more and more times with multiplication signs, you'd get to 4 to the 20th. But this is addition, which is very, very different than multiplication, right? So that one's not going to be right. If you picked answer B, make sure you know the difference between when you're adding terms with exponents and when you're multiplying terms with exponents. Very different. So I mentioned earlier that there's no coincidence that there's 4 of these 4 to the 5ths. And so what we can do right now is just imagine 4 to the 5th were like x. Guys, if you did this, I think you already know how you'd rewrite that. You'd say like, oh, that's 4 x's. And so that's the same principle here. We're going to say, but instead of x's, we have 4 to the 5ths. You still have 4 of them though. So you're going to say, I have 4 to the 5ths. And if you have 4 to the 5ths, well, think about how 4 to the 5th would be written. You'd write it as 4 times 4 times 4 times 4 times 4. And you are now multiplying all of that by another 4. So now you'd have 6 4s. This is literally 4 to the 1st times 4 to the 5th, which is 4 to the 6th. 4 to the 6th. What? Typo. I don't see 4 to the 6th. 4 to the 6th can be rewritten a number of different ways. Okay. But you see we have options of base 4 and base 2 here. So what we're going to do is we are going to rewrite 4 as a power of 2. 4 to the 6th is the same as 2 squared to the 6th. And from our exponent rules on the previous page, we know that when these are kind of raised to higher and higher powers, we multiply the exponents like this, 2 to the 12th. This is also, remember how we estimated this as being about 4,000. I like to tell my students, you all should definitely know your powers of 2. I don't know why my pen is doing that, but you should definitely know your powers of 2 through 2 to the 6th. If you're gunning for a 700 level score, I would say just go ahead and memorize that through 2 to the 10th. 2 to the 10th, 2 to the 10th is a nice benchmark. It's right around 1,000. It's 1,024. And if you know 2 to the 10th is 1,024 or about 1,000, you know 2 to the 10th is too small. We already said these were way too big. 2 to the 20th would be 2 to the 10th squared. So 1,024 squared, that's about 1,000,000. That's too big. And you can see 2 to the 12th is going to be this times 2 times 2, which is right around 4,000. Good stuff. Any questions in chat here? Again, like if they had given you, if they had stopped the sequence here, this is not going to be as clean. So like I said, there were 4 terms for good reason there. Nice. All right, let's go to the next one. Maybe I'll have you guys pull into here. I can go quickly back. All right, someone asked me about this one again. Yeah, okay, so let me just make sure this is super clear. Let's solve. Yeah, sorry, I'm looking at chat. Let's imagine this were x plus x plus x plus x, right? You would write that as, oh, there's 4 x's. Okay, and so for the same reason that we had 4 of these terms, and you're just like, instead of adding them, I'm just going to multiply 4, how many terms there are, by the value, 4 times x. Here, I'm going to do the same thing. I'm going to say, oh, there are 4 of these terms. There's 4 to the 5ths. And so instead of adding them all, I'll just do this, right? It's like if you have, 8 plus 8 plus 8, you would just say, oh, there's 3 8s. That's 3 times 8. And so that's all I'm doing here. Okay. And so 4 to the 5th is 4 times 4 times 4 times 4 times 4, and you're multiplying that by 4. And so actually, you don't even need these parentheses anymore, right? No. 4 times 4 times 4 times 4 times 4 times 4. That's 4 to the 6th. There it is. Okay. So hope that cleared it up. All right, on to the next one. Go ahead and poll in your answer here. I launched this poll. Go ahead and poll in your answer. You don't have to tell it in chat. Just fill it out in this anonymous poll. Okay, definitely haven't gotten all the answers. I'm running at about 40% here, but there's a lot of you. That's good. Okay, so one answer is kind of running away with it here, so I can afford to kind of speed up, I think, a little bit here. Just go ahead and, yeah, if you're watching in browser, you probably won't be able to see the poll. So I'm sorry about that. If you don't see the poll, just go ahead and tell me in chat what you got. Guys, we have no business knowing what these are. I mean, I guess you could figure out what 50 to the 3rd is if you know what 5 to the 3rd is, but we have no business knowing what 3 to the 10th is on this exam. 90 to the 5th, like, We see these giant terms and we have to immediately tell ourselves, oh, I don't actually have to calculate these gigantic numbers. There are going to be a lot of things that cancel out in this fraction, because look at the answer choices, like none of the answers are gigantic. There's a lot of reduction that's going to go on here. So when you have these larger numbers raised to powers, one of the best things to do is rewrite those larger numbers as products of smaller numbers. And it's usually best to go to the prime level if you can. So I'm going to rewrite 50 as 25 times 2, and actually say, well, 25 times 2 is 5 squared times 2. 3 is prime already, so I don't need to worry about 3 anymore. But let me see about 90. How is 90 going to break down into smaller factors? What's the prime factorization of 90? Tell me in chat. You know it's got a 5 in there and a 2 because it ends in 0. Yeah, pretty good. I mean, you could say, oh, this is 9 times 10, and 9 is 3 squared, and 10 is 2 times 5. So what we're going to do is we're going to rewrite this fraction all in little primes and then see what cancels out. Okay, so I'm going to rewrite 50 as, I usually like to write them in like ascending order. Just like when I have lots of variables and they're multiplied, I tend to like to write them in alphabetical order, but it doesn't really matter here. 50 to the third is the same as 2 times 5 squared, all to the third. 3 to the 10th. And 90 is 2 times 3 squared times 5. And we have 90 raised to the 5th power. All right, now we have to apply these kind of cascading exponent rules. So this will be 2 to the third times, not 5 to the 5th, but 5 to the 6th. And then times 3 to the 10th. All right, again, what is that number? I have no idea. It's way too big for me to handle. Okay, but I have faith that it's going to cancel out with a bunch of this other stuff in the denominator because these answer choices are suspiciously small. 2 times 3 squared times 5 all to the 5th. Apply your exponent rules. That's 2 to the 5th times 3 to the 10th. That's convenient. And then 5 to the 5th. Let's do some canceling. 3 to the 10th up top. No point in multiplying by 3 to the 10th. If you're just going to divide by 3 to the 10th, those just annihilate. 5 to the 6th up top and 5 to the 5th below. Well, that means I can get rid of 5 factors of 5 up here, right? I could rewrite 5 to the 6th as 5 to the 5th times 5. And that means these cancel. And then take a look at the 2's. 3 factors of 2 up top, 5 factors in the bottom. That should leave 2 left over in the bottom. Again, you could rewrite 2 to the 5th as 2 to the, maybe you can rewrite it. I'm having a trouble rewriting it myself. That's supposed to be a 3. Yes, a new stylus. 2 to the 5th is the same as 2 to the 3rd times 2 squared, and that allows us to cancel out the 2 to the 3rds. We're left with 5 over 2 squared, or 5/4. Answer D. Good stuff. Yes. 3 squared times 5 squared. 3 squared times 5 squared is 225. Yes, that would be 3 times 5 all squared, or 15 squared, or 225. So we know there has to be a factor of 2 in here. Oh, yeah, there has to be a factor of 2 in here because 90 is even. Okay. All right, thank you to Jaydeep and Sato and McKenna and Parth, who all gave me the prime factorizations of 90 in there. Awesome work, guys. All right, now we're going to get on to some slightly harder problems. Next one. Yeesh. Go ahead and let me know in chat, since the poll didn't work. Let me know in chat what you're getting for this one. Yeah, I realize actually a lot more people in the webinars watch this in browser and not in the app. And if you don't know, just say, I don't know. I'm not sure. I got lost on this one. That's totally cool. Thank you. Thanks for being honest. Yeah, I mean, you know what? This is a harder question than the other ones. If you don't know this one, that's fine. We're trying to leave it. Yes, I like it. I don't know yet, but I'm excited to find out. And I'm excited to tell you the answer. Very good. Okay, so in a problem where you have, I would say, like different exponents, right? So different exponent sizes. We have 2 to the n plus 1, or 2n plus 1 as a power, and just 2n, right? When we have powers of different sizes and they're not being multiplied, right? Because we could do that, like x to the 3rd times x to the 5th. We just say, oh, we could just add those exponents. That's x to the 8th. But here, these aren't being multiplied. These entire terms are being added or subtracted. generally the best move here is to factor out something in common, okay? So what we want to do is find something in common in both of these terms. And you know how we factor out like generally the largest factor to make things easier? That's what we want to do here as well. It's just like a little bit tougher to see the largest factor. You could say, well, I know those are both divisible by 5, and you'd be correct. But these are potentially both divisible by 5 a lot, right? You know, there might be multiple 5s in each of these, right? These are both kind of powers of 5. So what we're going to want to do here is try to factor out more than just 5, but a power of 5. And so I will say, this is the power of 5. I know 5 to the 2n is common to both this and this, right? Say, what would I have to multiply? We'll do this one first. What would I have to multiply 5 to the 2n by to get 5 to the 2n? 1, right? So when you distribute this times this, you should get this term. Now think to yourself, what would you multiply by 5 to the 2n to get 5 to the 2n plus 1? You'd multiply it by another 5, right? Because this is like 5 to the first, right? 5 to the 2n times 5 to the first is 5 to the 2n plus that 1. And now we just need to get this negative sign in the middle because this is really minus 5 to the 2n. And so this is how we want to rewrite the left side of that equation. All right, we recognize, okay, I've got different bases here. Or sorry, I have the same base, but I have different exponents. And I'm not multiplying, I'm adding or subtracting. That's our kind of sign to factor, our clue to factor. All right, that's equal to 10 squared times 5 to the 10th. All right, well, we know what 5 minus 1 is. 5 minus 1 is 4. So this becomes 5 to the 2n times 4 equals. And now we need to do something with this 10 squared. All right, let's do something with this 10 squared and rewrite it as 5s and 2s, right? We have different kind of size bases. Let's try to get them to their prime ingredients, just like we did in the previous problem with 50 and 90. This is 5 squared times 2 squared. And we still have 5 to the 10th. This is really useful because 2 squared and that 4, which was 5 minus 1, cancel. That's really hard to see here. It's hard to see that there's a factor of 4 in both sides, but that's why we factor out the largest exponent term and the 4 just kind of emerges. So now we've got 5 to the 2n equals 5 squared times 5 to the 10th. That's 5 to the 12th. The only way that the left side can equal the right side here is if the powers are the same. This is back in the day, you'd hit the logarithm button on the calculator or something. We don't have that button, but we do know that in order for the left side to equal the right side, 2n has to equal 12. And if 2n equals 12, n equals 6. If you said answer B, nice job. This is not an easy problem. Great job. JD asked, like, what if these powers had been negative? Yeah, what if this power were like negative 2 to the n plus 1, and this one were 5 to the negative 2n? Would I factor out, which one would I factor out? I would say it probably wouldn't matter. You just need to know how to factor it out and then see what this resultant value leaves you with on the right side. If you end up factoring out like if we had done that here, okay, we could actually just, we should be able to just change this. Right, stick with me, guys. We're going into uncharted territory. If you had decided here, oh, let's get rid of that. If you had decided here that you were actually going to factor out not 5 to the 2n, but 5 to the 2n plus 1. Like, that's doable. You would just say, oh, the first term would be 1. And what would the second term be? Like, what times 5 to the 2n plus 1 would give you this? Well, you want to get rid of this plus 1, so that would be 5 to the negative 1. And then we keep this over here. That's 5 squared times 2 squared times 5 to the 10th. What's 5 to the negative 1? That's a fifth, right? A fifth. And 1 minus a fifth would be 4/5. So you'd have 5 to the 2n plus 1 times 4/5. You could actually see here that this 5 should cancel with that, right? There's a factor of 5 that would cancel with this factor of 5. And you could solve it from there and get the same thing. Yeah. Alternatively, you could just, here, let me just go ahead and finish this out. This should be 2 squared. Multiply both sides by 5/4. Cancel this. This divided by 4 cancels with that, and now that becomes 5 to the 13th. And now we have 5 to the 2n plus 1 is 5 to the 13th. Solve for n the same way. You'll still get n as 6. Yeah. Good. All right, let's go ahead and move on. I'm getting like lots of questions, but they're good, but I just can't afford to answer them all. Maybe a little bit later. All right, last one. Go ahead and tell me in chat what you got for this one. All right, a lot of flurries in chat. Good. It looks like a lot of us are on a couple of different answers here. I think there's a couple of ways to do this. Okay, I think you could actually solve for x and y here. Okay. And you'd say, oh, 400. What is 400 as 4s and 5s? You say, well, 400 is 4 times 100, and 100 is 4 times 25, and 25 is 5 times 5. So apparently 400 is, when you break it down, 4 squared times 5 squared. And that makes sense, right? It's 20 squared, so it's 4 squared times 5 squared. Oh, if that's equal to 4 to the x, 5 to the y. The only way this works, if x and y are both integers, is if x is 2 and y is 2. And that would tell you then that x plus 1 is, of course, x plus 1, not x plus y. We would know what x plus y is as well, but that's not what this question's asking. X plus 1 is 3, y minus 1 is 1. And then we could actually do this. We'd say, oh, 4 to the x plus 1, that's 4 to the third. 5 to the y minus 1, that's 5 to the first, or just 5. And what's that equal to? 4 to the third is 64. I think we did that a little bit ago. 64 times 5 is 320. And you could get answer B that way. I don't think that's the most efficient way to do it. But I mean, I think you should know how to do it that way, ideally. Yeah, I know a couple people told me in chat that they actually did not solve for x or for y here. They just realized, oh, 4 to the x plus 1 times 5 to the y minus 1, that's the same as 4 to the x times 4 to the 1 times 5 to the y times 5 to the negative 1. And what do we say about negative exponents? Just write them as the positive version of the exponent in the other side of the fraction. So that's 4 to the x times 4 to the 1 times 5 to the y over 5 to the 1. And all we can do here is just rearrange the multiplication up top, right? That's 4 to the x, 5 to the y. And I'm grouping those because I know what that is. Times 4 to the 1 over 5 to the 1. Well, the ones don't matter. That's 4/5. So this should just be 4/5 of whatever this term was. 4/5 of 400. And 4/5 of 400 is, guess what, guys? It's still 320. And this could be like a little shortcut. And we could arrive at that shortcut if we just recognize how this +1 and -1 in these exponents work. Oh, I'm multiplying by 4 an additional time, hence the +1, and I'm going to multiply by 5 one fewer times, or divide by 5 once, and that'll get you to 320 as well. Good stuff. Okay, well, we are through some of the problems I had here. Yeah, some of the problems I had here, but there are more that I'd like to do. So, I think what I'll do, is, because I have questions in chat right now coming in, I'm going to put another question up on the screen, and you guys just need to mute me. All right, you need to mute me because I'm going to talk a little bit more about this one because someone had a question in chat. So if you don't want to hear my voice as we're going through this problem, or as you're working on this problem on your own, just mute me. I'll give you 2 minutes. You have 2 minutes to not listen to me. All right, so back to that previous one. That previous one, we said 4 to the x, 5 to the y equaled 400. And so we want to know what 4 to the x plus 1 times 5 to the y minus 1 is. All right, we just need to rewrite this, okay, and figure this out, okay, related to this. So I'm going to say that's the same as 4 to the x times 4, right? This is really 4 to the first power, and we multiply these things, we should get this. So I'm going to rewrite that 4 to the x plus 1 as 4 to the x times 4. I'm going to rewrite this as 5 to the y times 5 to the negative 1. But 5 to the negative 1 is 1 over positive 5. So instead of multiplying by 5 to the negative 1, what I'm going to do here is I'm going to multiply by a fifth or divide by 5. This is the same as this. Okay. Now I'm going to reorganize this and say this is the same as 4 to the x times 5 to the y times 4 all over 5. And so this is 400. This is like the whole point of using this. This is 400. So we have 400 times 4 over 5. Take your pick at how you want to do that. 1600 divided by 5 is 320. 400 divided by 5 is 80. Times 4 is 320. But that's kind of the principle there. Two minutes. All right. Unmute Jeff. Unmute me. All right. That has been just over 2 minutes here. Guys, what's 4 to the 17th power? You have bonus points if you know this. Yeah, I don't know this. We're going to need to do something else. What do we see here, right? We see powers, we see a negative sign. And so kind of like that previous problem, or I guess it was a few problems ago, right? I guess it was this one, and we factored something out. We're going to need to factor something out here. And like there's a clue that tells us we're going to have to do that. It's the word factor. All right. So we need to break this thing up into pieces. All right, guys, what should I factor out? Tell me in chat, what do I factor out? Got a couple different answers. I've got in ascending order. I have 2. I have 2 to the 24th, and I have 2 to the 28th. Yeah, I think what's going to be most helpful is to factor out the largest factor that's common to both of these. And you might ask yourself, like, how do I know which one's common to both of these? I could see that 2 is common to both of these because I know 4 has a factor of 2 in it. How do you know 2 to the 24th is a factor of both of these? Well, one other thing you could do is recognize when you've got different bases, right? When we've done this in the past, right? We had 50 to the third and 90 to the fifth and 10 to a power. We get them into their primes. And so we could write 4 to the 17th as 2 squared to the 17th, right? If we believe this, and we all should believe this, because 4 is definitely 2 squared, then we know our exponent rules tell us this is 2 to the 2 times 17, or 34th power. So this is, Heidi, check that again. So this is really 2 to the 34th minus 2 to the 28th. And now you can actually see, oh yes, 2 is definitely a factor, but it is not the largest factor. 2 to the 24th is a giant factor of both of these, but it's actually not the largest. The largest factor will be 2 to the 28th. What is 2 to the 28th? I don't know. It's like 1/4 billion. It's so big. I don't really care what it is. I know it's not my greatest prime factor because it's made up of a bunch of 2's. So we're going to factor out 2 to the 28th. What would you multiply by 2 to the 28th to get you 2 to the 34th? You'd get 2 to the 6th. All right, and this is where 2 to the 6th is kind of coming from if you think this is the largest prime factor. But what do you have to multiply 2 to the 28th by to get 2 to the 28th? You have to multiply it by 1. So don't forget this -1 bit. Yeah, that's super important. That's without it, we're not going to be able to get this right. Said earlier, 2 to the 6th is 64, -1 is 63. So this is 2 to the 28th times 63. And 63 is 7 times 9, or 7 times 3 squared. 2 is a prime factor, 3 is a prime factor, but 7 is the greatest prime factor. Yeah, there you go. Good stuff. Yeah, I mean, I think you, in the case of, okay, JD has a question like, what am I factoring out here? Am I factoring out, like, is it always the largest exponent? What if the exponents are negative? When the exponents are positive, I'm probably factoring out the largest one. Again, it doesn't really matter which one you end up factoring out, because the math will work either way, right? That's the great thing about math. It doesn't care like which way you do it, as long as each step is a legitimate step. So it doesn't really matter. I would say, like, if you're spending a lot of time thinking about what to factor out, like just pick one. Just pick one. Don't suffer from paralysis by analysis. Hold on a second. Sorry, good questions coming in here. Yeah, I mean, I would take out the 2 to the 28th here, because if I take out 2 to the 34th, I'm going to be left with a fraction in here, right? This would be, you know, if you do it, this would be times 2 to the -6, which is 1/64th. And I know, like, I have to be dealing with integers, I think, throughout here. Yeah, so that would save me some time if I didn't deal with fractions. Got it. Okay, so a question came in. Why can't I just take this and say, oh, 2 to the 34th minus 2 to the 28th, why isn't that 2 to the 6th? And I would ask you, like, let's just do this with an easier question. We should know what 2 to the 4th is, okay? And we should know what 2 squared is. Like, is that equal to 2 squared? Can we just do 4 minus 2 is 2? 2 to the 4th is 16. 2 squared is 4. That's equal to 12, which is definitely not 2 squared. So we don't get to subtract our exponents here, okay? We get to subtract the exponents here. This is the instance where you subtract the exponents and get, oh, this is the same as 2 to the 4 minus 2. Not here. And the way to kind of check that is, again, like you probably don't want to check it here because these numbers are so large. Like, do you know what 2 to the 28th is? Are you actually going to subtract that from here to check? No one is. But you can just check it with some easier numbers and see if the principle works. And if the principle doesn't work here, then it won't work here. Yeah. All right, we're gonna do one more problem. Geez, I have so many problems here. So many exponent problems. But I did say we were gonna do some more number property stuff, and so I don't wanna be a liar. So we're gonna do this one, and this might be the last one. A question came into chat. I will try to answer it on the screen as you guys are working on this. Just pay no attention to me as I'm typing stuff on the screen. Give you another minute here. Oh, this is a data sufficiency problem in case you couldn't tell. It's been a little over 2 minutes. Go ahead and take a little bit more time to think through this if you want. Question came in about like what things to memorize related to exponents. And I don't have like a great rule on this, but I think if you have your perfect squares memorized through 20 to the second power, that's largely helpful. Like how often are they going to ask you what 19 squared is? You know what? Not very often. 19 squared, probably could get rid of that. But I don't know. Like I've seen instances of them like asking something like this, like or as part of a question, like part of the question involves like 17 times 19. And I would say like if you know what 18 squared is, this is really easy because this is 18 minus 1 times 18 plus 1. And that's through the difference of squares, 18 squared minus 1. And if you know what 18 squared is, then guess what? You know what 18 squared minus 1 is. And so that would be pretty, like, that's like a nice shortcut to have. Yeah, perfect cubes, I would say like knowing through 6 cubed, that's good. I'll tell you like the number 216, which is 6 cubed, like you'll occasionally see the number 216. And when you see it, you kind of want to be able to know like, oh, that's 6 to the third. Like it's probably not coincidence that they're using that, and it's not related to some factor of 6 question. Like you'll see 216 on the GMAT occasionally. You probably won't see 217. It's just not a number that like comes around very often, but 216 does. Yeah, there's like 216 is 6 to the third. Yeah. So yeah, I don't know, like if you do enough calculations, you'll see the number 288 on the exam sometimes. 288 seems weird, but 288 has lots of factors in it, right? It's 16 times 18. It's like all lots of 2s and 3s. So it's like a number that occasionally will pop out, like 287. It's a trash number, I know, I'm just kidding. All right. Number properties and exponents, specifically positives negatives, right? Greater than 0 and exponents. When I see a question like this that involves exponents and positive negative talk, there's like one thing I need to think about primarily, and that is things raised to an even power aren't negative. Okay, say that again. Things raised to an even power are not negative. And in this problem, they're not 0 either, right? If I know this whole expression is greater than 0, then A is not 0, B is not 0, and C is not 0. Okay. So I now know that C to the 4th is positive. So here's what I'm going to do in this problem. From like a top level point of view, I see that this is about exponents and positive negatives. And so I know that I'm going to have to deal with some sign issues and exponents. The other thing I see is the statements are actually very easy. Well, they're very short and simple, right? B is positive, C is positive. And so what that tells me is like, I need to spend more time up here. Like I really don't need to worry about these statements that much right now at all. The difficulty in this problem is not the statements. So I'm just going to, once I recognize that they're pretty simple, I'm going to ignore them for now. And I'm going to spend my energy here. All right, so first, let's figure out what this is really telling me. Right? Why are they giving me this condition? It's like statement 0. It's like a clue, right? And I want to be, I want to comb over this clue and try not to miss anything. Yeah, JD, that looks right. So let's go ahead and write this down again. A, B to the 3rd, C to the 4th is greater than 0. I know that C to the 4th is positive. Okay, convince yourself that C to the 4th is positive here. Okay, can't be negative. Imaginary numbers are not a thing on the GMAT. And when the quant instructions at the beginning, it tells you all numbers are real. Don't have to worry about those I's here. C to the 4th can't be 0 because the product is not 0. So it's got to be positive. And what that means is in order for this whole left side to be positive, that means that this needs to be positive. So this tells me A, B to the 3rd must be positive. All right, if A, B to the 3rd were negative, then negative times C to the 4th would be negative, which doesn't happen here. So A, B to the 3rd is positive. And now what I'm going to do is I'm going to just try to filter out, siphon off even powers of B. I'm going to say this is the same as A times B squared, and that's greater than 0. Guys, C to the 4th was positive. B squared is positive, right? Convince yourself that this has to be positive, and that therefore AB is positive. So this first little clue is really telling you that AB, not AP, AB is positive. And that is very valuable information here. Because now that I know AB is positive, now I want to shift my attention to this question. What about A cubed B C to the 5th? I want you to focus on this step here, this step. I took this odd power of B and I just extracted some even powers of B because I know even powers of B are positive. Try doing that here, not to B, but to A and C, and see what happens. It's pretty good. Yeah, so I'm going to rewrite A. It's kind of if I rewrite B to the 3rd here as B squared. I'm just going to write this as A squared. I'm going to write C to the 5th as C times C to the 4th and ask, hey, is that greater than 0? C to the 4th is positive. So is A squared. So again, those don't really matter here. They're going to preserve the sign of everything else. So another way you could think about this is I'm just going to reorder the a, b, and c that are kind of left alone here. The a squared, the c to the fourth. Say, look, all of this stuff is positive. So in order for this entire thing to be positive, right, is it positive? These would have to be positive, right? Because that would allow you positive times positive is greater than 0. So this question now turns into, is A times B times C greater than 0? And now we're going to consult our first clue. This tells you that A and B are positive. And so for A times B times C to be positive, C would have to be positive. Is C positive? That is what this question is really asking. That's a lot of work, right? But it's actually pretty quick if you feel good about these rules. C to the fifth will have the same sign as C to the first. A to the third will have the same sign as A to the first. A to the third, A to the seventh, A to the 11th, A to the first, all have the same sign. Odd powers preserve sign. And that's why I'm just like kind of rethinking about A cubed as A times A squared, where A squared doesn't really matter here. Okay. So is C greater than 0? Let's look at statement 1. B is greater than 0. That doesn't answer my question. Statement 1 is not sufficient. Answers A and D. Get out of here. Let's go take a look at statement 2. Oh, what do you know? C is greater than 0. Statement 2 is sufficient. On its own, statement 1 is not. This is answer B. Okay. So a little bit of exponent rules applied to some number property things as well here. You can see the positive and negative things happening here. You can see the odds and evens in effect. This is kind of, where the GMAT gets harder and harder questions from. They take multiple topics and kind of shuffle them or blend them together in one problem. All right. I'll tell you what, we've gone a little over time, but I don't know if you got my email. I emailed everybody on the roster for free GMAT prep hours, hundreds of people. And I asked, are there any exponent questions that you guys have from your studies? And someone sent me one, and it is from a not free resource. So what I did is I took that problem and I made a new version of it. And I will present that to you here and a way to think through it. And so we're going to go a little late tonight. If you got to leave, that's fine. If you want to stick around, that's cool too. Give you a couple minutes to think about this, and we'll dive in and we'll wrap things up. It's been a minute 15. It's been just over 2 minutes. I'll give you another 45 seconds here. I'll give you 3 total minutes here. It's been 3 minutes. All right. Okay, so this problem, so the original problem that this is based on is already hard, and I made it more difficult, I would say. So if you missed this one, that's okay. If you got it, that's really, really great. So express as a terminating decimal. By the way, in order for a decimal in base 10 to terminate, and you're only ever going to be dealing with base 10 on the GMAT, I think. In order for a decimal to terminate, the numerator, I guess. Let me make sure I've got that right. No, the denominator. The denominator can only have factors of 2 and 5 in them, in it. Yeah, my verbal skills go out the window as I'm doing these quant calculations. Yeah, because decimals are based on groups of 10, right? Deci, 10. And 10, like the way you can chop up tens, like without having fragmented decimals, is by chopping them in half, right? 0.5 and 0.5, or chopping them in fifths, 0.2s. That's it. If you chop them in thirds, you get repeating threes. If you chop them in sevens, like you get the 1, 4, 2, 8, 5, 7 repeating pattern. In order for a decimal to terminate, its denominator of the fraction should only have factors of 2 and 5 in them. So that's kind of a clue here. All right, we can only be left with 2s and 5s, but I see like 3s in places. Those are going to have to go. Okay. So what we're going to do here is we're going to rewrite x as all primes, right? We're going to say x is 2 times 3 over 2 squared times 5 to the 5th. And 5 to the 5th. That's a 5, not a 6. We're going to say y is 3 over 5 to the 3rd. And we're going to have to break down this 12 a little bit. 12 is 2 times 2 times 3. And so we're going to raise that all to the 2nd power. All right, let's see what we can do here. One of the factors of 2 here will cancel. And so this will be 3 over 2 and 5 to the 5th still. Y will be, well, let's go ahead and get a sub-step in here. This will be 3 over 5 to the 3rd, and then 2 squared, 3 squared. So this 3 should cancel with one of these 3s. So there's nothing left on top except a 1. 2 squared times 2 squared is 2 to the 4th. There's a factor of 3 as well. Come on. There's a factor of 3 as well, and a bunch more 5s. So x is this, y is this. We're going to have to multiply these. Let's just go ahead and write it like this and say, oh, I multiply straight across. So that's going to allow me to just kind of bridge this gap here. The 3s will end up canceling out, so we are left with no more 3s. And this should become 1 over 2 to the 5th, 5 to the 8th. Well, that was fun. That's a lot of work, and we're still not done yet, okay? Still not done yet. But we do have a much kind of simpler fraction to work with. And what do you know? It only has 2s and 5s in the denominator. So this should be able to reduce to a terminating decimal. All right, so what we're going to do is I'm just going to take all this. I'm going to move it over here for now while I delete the rest of this and figure out what we're going to do with this still kind of ugly expression. Any ideas from you guys? What can I do with this? I need to simplify it even more. That is such an interesting move. Yeah, like all today, what we've been doing is we've been taking bigger numbers and breaking them down into their primes, right? We took 50 and chopped it into 5 squared times 2. We took 90 and chopped it into 2 times 3 squared times 5. We've got the primes here, and now I'm getting suggestions to group them back into tens, and that is indeed going to be very wise, all right? So we are going to say, oh, this is the same as 1 over 2 times 5 to the 5th, right? Because that's 2 to the 5th, 5 to the 5th. And there's still like some leftover 5s in the basement. That's the same as 1 over 10 to the 5th times 5 to the 3rd. And that's the same as 1 over 10 to the 5th times 1 over 5 to the 3rd. 1 over 10 to the 5th, all that's going to do is move the decimal place, right? It's going to add some zeros in this case because we're dividing by powers of 10. We're just going to keep adding kind of zeros to the front of this number and making the decimal smaller and smaller. But we want non-zero digits, right? So really, this isn't really going to matter. Let me hold on one second. I'm reading something in chat real quick. That's correct. We can only make 5 tens because it's like we are constrained here by the 2s. The 2s are our like limited ingredient, right? For every to make a 10, you need a 2 and a 5. You have a plethora of 5s. You are kind of limited on the number of 2s. So the 2s are going to limit how many 10s you can make. Since there's only 5 2s, we can only make 5 10s. That's the way to think about it. Good. Yeah. It's like if you were, I don't know, people are still baking a lot, but like, people have lots of flour and only a few eggs. Guess what? The eggs are going to limit how much bread you can make. Do you make bread with eggs? I have no idea. Okay, this is exponent class, not cooking class. All right. Hold off on this. This doesn't really matter. 1 over 5 to the 3rd. Yeah, someone told me in chat that is 1 over 625. That is true. Or sorry, 1 over 125. And I would say that is true. What is a 1 over 125 as a decimal? Do you know? So I think what I would do here is, I would probably just start busting out some division and just say, oh, 1/5 is 0.2. Okay. And if I divide this by 5, what is 0.2 divided by 5? I should get 1 over 5 squared. What's 0.2 divided by 5? One way to divide by 5 is to divide by 10 and then double it, right? So divide by 10 and then double it. So 0.04. So then 1 over 5 cubed would be this divided by 5. What is that? Divide it by 10 and double it. Oh, that's 0.008. That is 1 over 125. Not easy to see. Okay, so this is going to be equal to 1 over 10 to the 5th times 0.008. And I don't really know if you want that leading zero. It doesn't really matter here. I for some reason never write it, but it might be because I'm lazy. Guys, when you multiply this by 1 over 10 to the 5th, all you're going to do is just keep adding zeros in front. You're going to move the decimal to the left, keep adding zeros. And so all you're going to be left with in terms of non-zero digits is this single 8. Not what is the digit, how many digits are there? This one's going to be answer A. There's only one. Yes. Thank you for the question, Sherful. All right. That was a lot of exponent stuff. I hope you guys feel more empowered when it comes to tackling this problem. Any questions from you guys? Why is it 1 again? Yeah, because when you do all the division, all you're left with is a lone 8 after a bunch of zeros. It says how many non-zero digits are there? It has a bunch of zeros. Those don't count. All right, let's just go ahead and back through this again. Yeah, 1 over 125. That seems like to be, that's where some of the issues are coming. Yeah, 1 over 125 is not 0.125. That's why I put this answer in here, because it looks tempting, right? Just like 1 over 2 is not 0.2, right? Like you wouldn't say 1 over 2 is 0.2. You all know this. Again, this is kind of what I'm saying. Like if you're not sure if this is how it works, like just try it with a much easier number, right? Right? When we said like, is 2 to the 34th minus 2 to the 8th, 2 to the 6th? Are you allowed to subtract there? Like test it out with some easier some smaller, easier, aka smaller numbers. So like, is 1 over 2 0.2? No. Like, is 1 over 7 0.7? No. So 1 over 125 is not 0.125. This is an eighth. This is actually a percentage or a fraction or a decimal. You should know. This is 1/8. And that is not a coincidence why the digit ends up being 8 here. Okay, there is some symmetry between 125 and 8 when it comes to powers of 10. All right, so we said 125 is 1 over 5. Divide that by 5. Divide that by 5. So this is really like 1 over 5 over 5 over 5, right? Start small, keep going. 1 over 5 is 0.2, right? We need to know that. 0.2 divided by 5 is 0.04. Okay, and just check. 0.04 times 5 is 0.2. And then 0.04 divided by 5 is 0.008. Again, I like to just divide by 10 and then double. That's the same as, right, because 2/10 is the same as 1/5. So this is why the last digit is 8, and it is the only non-zero digit. Cool. Yeah, I'm checking on the calculator. Just try like 1/5 divided by 5 and like see these steps. Yeah. All right, guys, I think we're going to close things up here. Thank you so much for all your questions and for your participation today. I hope to see you at the next event I do in December, although you should go to the very next event that is in earlier December with, oh, I don't even know who's doing it. I don't know, Reed might be doing it. I don't know, Reed does a lot of them. Awesome, thanks so much for your comments. Guys, have a great holiday if you're celebrating that this week. Be safe out there. I'll see you next time. Bye, guys. Appreciate it. Thanks for watching the YouTube video too.